Light reflection and refraction. As we know that light is a form of energy. Light is needed to see things around us. We can detect light with our eyes. Light enables us to see objects from which it comes or from which it is reflected. We will discuss some of the phenomena associated with light, such as reflection and refraction. Properties of light. Although light seems to travel in straight lines, however, there are two theories about the nature of light: the wave theory and the particle theory. According to wave theory, light consists of electromagnetic waves which do not require a material medium for their propagation. On the other hand, according to particle theory, light is composed of particles which travel in a straight line at a very high speed. Thus, the light has a dual nature. Light exhibits the properties of both wave and particles. The modern theory of light, called quantum theory of light, combines both the wave and the particle models of light. We will now discuss about the phenomena of reflection using the straight line propagation of light. Reflection of light, the process of sending back the light rays which fall on the surface of an object, is called reflection of light. Laws of reflection. The angle of incidence is equal to the angle of reflection, and the incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane. Image formation by plane mirror. Image is always erect, virtual, and laterally inverted. The size of image is equal to the size of the object. Spherical mirrors. There are two types of spherical mirrors: concave mirror and convex mirror. Before discussing the image formation by spherical mirrors, we need to recognize and understand the meaning of few terms. These are the pole, the center of curvature, the radius of curvature, the focus, and the focal length. Now let us see the diagram of concave mirror and convex mirror to understand these terms clearly. Since the spherical mirrors are the part of a hollow sphere, so the center of the curvature of a spherical mirror is the center of the hollow sphere of the glass of which the mirror is a part. You can see in the figure, C is the center of curvature of the concave mirror, and C the center of the curvature of the convex mirror also. But the center of curvature is not a part of the mirror, because it lies outside the reflecting surface of the mirror. In case of concave mirror, the center of the curvature lies on the front side, whereas in case of the convex mirror, it is behind the mirror. Then come to the pole. The center of a spherical mirror is called its pole, which is represented by P letter in the diagram. P is the pole of the concave mirror, and P is the pole of the convex mirror also. The pole of a spherical mirror lies on the surface of the mirror. The straight line passing through the center of curvature and pole of a spherical mirror is called its principal axis, which is denoted by XY. Now the aperture. Aperture is that portion of a mirror from which the reflection of light actually takes place, and it is denoted by mm dash. Now come to the focus. It lies in the midpoint between the pole and the center of curvature. As you can see in the diagram, in case of concave mirror, all the reflected rays are meeting at a point on the principal axis of the mirror, which is the focus of the concave mirror and is denoted by capital letter F. In case of concave mirror, the focus lies in the front side of the mirror. In convex mirror, all the reflected rays appear to come from a point in the principal axis. This point is called the principal focus of the convex mirror. It lies behind the convex mirror and is represented by letter F. The distance between the focus and the pole of the mirror is called the focal length. There is a relationship between the focal length and the radius of the curvature. The radius of the curvature is equal to the twice of the focal length. Don't forget this relation because it is very important on the point of view of numericals. Whenever you will do the numericals, you will need the help of this relation. Now let's start the representation of image formation by spherical mirrors using ray diagrams. There are certain rules for obtaining images in the concave mirrors and the convex mirrors. Let's see the image formation rule for the concave mirror at first. As you can see in the diagram, a ray of light which is parallel to the principal axis of a concave mirror, it is passing through its focus after reflection from the mirror. So the first rule is the rays which is parallel to the principal axis always passes through the focus after the reflection from the mirror. As you can see in case of the convex mirror, a ray parallel to the principal axis appear to diverge from the principal focus illustrated in the figure. According to the next rule, a ray passing through the principal focus of a concave mirror after reflection will emerge parallel to the principal axis. In case of convex mirror also, a ray passing through the principal focus after reflection will emerge parallel to the principal axis. In the next rule, a ray passing through the center of curvature of a concave mirror after reflection is reflected back along the same path because the incident rays fall on the mirror along the normal to the reflecting surface. On the other hand, a ray directed in the direction of the center of curvature of a convex mirror after reflection is reflected back along the same path. As per the fourth rule, a ray of light which is incident at the pole of a concave mirror is reflected back, making the same angle with the principal axis. In case of convex mirror also, a ray incident obliquely to the principal axis towards a point P will be reflected back obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence, making equal angles with the principal axis. In all the above cases, the laws of reflection are followed. At the point of incidence, the incident ray is reflected in such a way that the angle of reflection is equal to the angle of incidence. Now let's see the image formation by concave mirror with the help of ray diagrams. Let's consider the first case in which the object AB is kept in the infinity. As you can see in the ray diagram, we have drawn the rays parallel to the principal axis. Since ray parallel to principal axis passes through the focus, both rays meet at focus after reflection. Hence, image is formed at focus and is very small. Thus, we can say that here the image is highly diminished, point-sized at focus, real and inverted. In the second case, the object is placed beyond the center of curvature. At first, we draw a parallel line to the principal axis, so it passes through focus after reflection. We draw another ray which passes through center of curvature and is reflected back in the same path. Both the reflected rays meet at point A' and the image formed is A', B'. This image is formed between C and F, that is the center of curvature and the focus. The image formed is diminished in size, real and inverted. In the third case, object is placed at center of curvature C. At first we draw a ray parallel from the point A of the object to the principal axis. After reflection, it passes through the focus. Secondly, we draw another ray from point A of the object passing through the focus, which runs parallel to the principal axis after reflection. Both the reflected rays intersect at point A dash. Thus, the image A dash B dash is formed at C, that is the center of curvature. The image is of the same size, real and inverted. In the fourth case, the object is placed in between the center of curvature and the focus. At first, we draw a line parallel from point A of the object to the principal axis, which passes through focus, and another line passing through the center of curvature. Both the rays meet at point A dash, and the image A dash B dash is formed beyond center of curvature C. The image formed is enlarged, real and inverted. In the fifth case, object is placed at focus. We draw a line from the point A of the object parallel to the principal axis. After reflection, it passes through the focus. We draw another line from the point A after reflection, which passes through the center of curvature. Since both the reflected rays are parallel to each other, so they never meet each other, and thus the image is formed at infinity. The image formed is highly enlarged, real and inverted. In the last case, the object is placed between the pole and the focus. At first, we draw a line from the point A, which after reflection is passing through the center of the curvature. Then we draw the next line, which falls obliquely at the point B, that is the pole of the mirror, and is reflected back following the laws of reflection. We observe that both the reflected rays are diverging. It means that they would have met at some point. Hence, we extend both the reflected rays behind the mirror. We see that the reflected rays forms an image behind the mirror. Thus, we can say that the image is formed behind the mirror, which is enlarged, virtual and erect. Now let's see the mirror formula, which is 1 by f is equal to 1 by u plus 1 by v, where f is the focal length, u is the object distance and v is the image distance. This formula is valid in all situations for all spherical mirrors for all positions of the object. Now the magnification. Magnification is the ratio of the height of the image to the height of the object. So m is equal to height of the image, which is represented by h dash divided by height of the object h. So m is equal to h dash by h, which is also equal to minus b by u, where b is the image distance and u is the object distance. The height of the object is taken to be positive as it is placed above the principal axis. The height of the image should be taken as positive for virtual image. However, it is negative for the real image. If the value of the magnification is negative, that means the image is real. On the other hand, if it is positive, then the image is virtual. While solving the problems related to the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the new Cartesian sign convention. According to this convention, the pole of the mirror is taken as the origin from where all the distances are to be measured. All the distances measured to the right of the origin are taken as positive, while those measured to the left of the origin are taken as negative.